Hi, welcome back to CS170, week 5. We're going to be kicking off with algorithmic thinking. So let's just get right to it. So for this lecture, we're going to cover what is an algorithm and the difference between a program and an algorithm. It's a little bit of a minor point, but it's one of the points to cover. And the different properties of algorithms. The flowcharts and pseudocode we'll cover in another lecture. So I'm going to try to just keep it to the algorithm and heuristic processes for this lecture. So let's get into this. Okay, so what's an algorithm? Or actually, I should say, what's a program? Um, so probably would have done algorithm first and then program second, but we're starting off with programs. So programs, they're basically an implementation of an algorithm. Um, so algorithms could be a general thing to kind of say, okay, this is how I'm going to make a cake, right? So you have these ingredients, you do these sequence of events, mix them together, do whatever to set up the cake, put it in the oven, make sure the oven's preheated, blah, 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 all that kind of stuff. So there's your algorithm, and then how you actually execute it would be a program, okay? If you think back when we were doing the numeric conversions, a lot of times the computer science students will write a program in whatever language to implement some of these conversions. They could be doing some calendar logic, maybe calculating leap years. Maybe they can be, doing like, what are the month end dates for the next couple of years, something like that. Doing numeric conversions, converting like a binary number to a decimal number, stuff like that. And you can remember I was actually doing that with the Excel spreadsheet. So you can say that I was basically writing a program in Excel to do numeric conversion. So, this is what we're talking about when you say a program implements an algorithm. There could be different types of implementations, right? I can write in any number of different programming languages. Um, I can implement it. In my case, I was just doing some stuff in Excel. So that's what a program is. A program is an implementation of an algorithm. Okay. So like it says here, usually written in a specific programming language. Okay. And usually you're having a computer to complete the task or solve the problem. Okay, and so like I said, I just gave you an example of me doing the numeric conversions with the Excel spreadsheet. Okay. Okay. So, well, okay, here we go. Algorithm that we've learned, and one of them is converting binary to decimal. Okay. Um, so you remember if we have like a 1, you have that, whatever that value is for that position, you apply that to your decimal, right? So you remember we wrote like all the powers of 2, and then whatever like the decimal, whatever the binaries had for a 1 in that position, then you pulled all those down and then you sum them together, right? So that's what this is saying, right? So there's a 1 there, you take that in. If there's a 0, you write nothing, and then you remember that bottom line, we summed them all up, right? And that gave you the decimal value, right? So that's an algorithm for numeric conversions, okay? And then down here, they're talking about, other things like, I just happened to talk about a cake, so they're talking about a chocolate cake here, right? So you see all the ingredients, here's all the steps, you're melting the chocolate and the butter, you stir up the sugar, mix all this together, and you're gonna eventually bake after. You're gonna eventually bake and come out with a cake, right? Some of you may have played around with putting together stuff from IKEA. And you have like how to do laundry. Okay, so these are different types of algorithms examples. Okay, and yeah, I guess trying to be funny here. So we have a little picture here of a little traffic jam. I don't know where this picture comes from, but if I look kind of closely, it looks kind of like it's probably somewhere in China. I see something like up here. It looks like a little Chinese restaurant or something like that. Um, yeah, somehow they have this little thingamajig intersection here with no traffic light. So you can imagine what's happening there. Okay, so yeah, I guess what you would consider a bad algorithm. Okay, so what's the difference between an algorithm and heuristic process? So I think of a heuristic process as like a rule of thumb, right? So you can do something quick. And what I did was I pulled up this rule of 72. Okay, so for some of you, especially you go into business school, the rule of 72 is a simple way to look at an investment to see how long it will take to double your investment. Okay, and note this point right here. Right, it says investors get a rough estimate of how many years it will take to get the investment to duplicate itself. So you probably know, well, or you may not know, right? But we'll actually cover a little bit later. Like Excel has a whole bunch of different math functions in there, and one of them, well, some of them will be dealing with if I borrow money or I have an investment, and how it will grow over time. Okay, so you'll have like essentially how interest rate will take some value of something and how that plays out over time. So of course, that's going to be exact, right? So that'll tell you exactly how much money at whatever interest rate, or in this case, we're talking about an investment, a return on investment, but it's just basically a percentage, right? And then, or rate of return, I should say. And then you take that, and then eventually it's going to double itself, right? So you got an investment, let's say it's getting 10% return, okay? Well, then you divide the 10 into 72, and you're looking at about 7 years, right? So when I say about or roughly, that's what we mean by heuristic, right? It's just a quick calculation. It's roughly, it's not super exact, right? So that's what heuristic is. And so I'm not going to spend too much time on it, but um, that's just an example, right? So what it's saying here, not systematic, not guaranteed, um, so it's helpful to find like a result. It's an approximation. This is what I think is the key part here. This last sentence here where it says it's often an approximation for a solution. So it's very quickly, in my head, I came up with something on how quick it is you would take to double your investment. Okay, it's a good enough type of calculation a lot of times. And you can see that in all kinds of things in life, right? So, we're always looking for shortcuts, right? We want to make a quick decision. See something, do I make a left? Do I make a right? Am I in danger? Whatever it is, you do something quickly to evaluate the situation and make a decision, right? So we have heuristic processes all over the place. Um, we're not computers, obviously. So hopefully that gives you a kind of an example or a view of the difference between algorithm and heuristic process. Okay, so I wouldn't really sweat this one too much. It's not that big of a deal. I think the more important part is really to understand algorithms and just know that heuristics are a rule of thumb. Okay, so here are the different things that make up the algorithm. Number one, you have to have an input, right? So let's say I have um, I think we're going to be talking about calculating averages or something later, right? So part of that would be you have to have some input for your numbers to feed into the average calculation, right? So you have some input, right? That's going to be data that's going to come in. It's going to probably be stuff that will feed into a calculation, okay? Then number two, you're going to have an output. Okay, so what is it that you're going to do? What are you shooting for? Like in the earlier slides, I want a piece of cake, or I want a whole cake coming out. Um, so yeah, here we're saying algorithm to calculate a batting average, right? So like I was saying, for the input, I feed in some numbers, and I'm going to come out with an average, right? So that's what the output is. You want some sort of output. And finiteness, okay? So you want to have some sort of endpoint that would come out. So let's say before I was saying, well, I want a cake, right? That's my output. Um, there will be certain types of things where if you don't have a finite output coming out, then it's not really a valid algorithm, okay? So one thing here, like it says, it's talking about infinite loop. Okay, maybe you think of something like, you know, calculating pi, right? So that's gonna go off to infinity. It will never end, right? Sometimes we can write a program that will continually keep on running forever unless you stop it, right? Um, so that's not much of an algorithm. Algorithm wants a finite outcome to come out, right? So either you get your expected output, or it'll tell you no solution is possible, right? In our case, when I said calculate out pi, you could say, well, I'm going to calculate pi out to however many digits, and then boom, that's it. So the fact that pi calculation goes out forever is not the reason why you're saying it's not an algorithm. It's the fact that you don't ever let it stop. Okay, so uh, when I say expected output or no solution possible, the fact that I said, okay, I want to calculate pi out to whatever, 10 digits, well, then that's my expected output. Okay, and that's my algorithm. Okay, but if you just go out there and say, I'm going to just calculate pi, uh, and then it's just going to continue on forever, then it would just never stop. The computer would just keep on churning. Okay, nothing will happen. It would just sit there and you don't know what the heck is going on, right? So, you know, what they call definiteness. I don't even know if that's a real word, but definiteness, definiteness, okay? Algorithms can specify every step and the steps that have to be taken in a process, right? So it's very exact. So this is what you need to be able to translate this into code, right? If you don't have this, then there's no way you can translate into something that the computer can do. All right. So computers have not gotten so far in terms of their artificial intelligence that you can give it like very vague types of steps. You have to give it very concrete steps, sequence of steps to do. Okay. And this is pretty interesting here on you know, how to handle certain things, like how to handle errors, right? So if I program something, let's say, to add numbers, right? So I have a program add to numbers, but you know, when people put stuff in, uh, you have to have some way to manage the fact that they may not put in a number. Maybe they'll put in like an ABC or something like that. So part of your process would be to handle that, right? So either one, have something up front to prevent them to put it in, or two, as it comes in, we have a check to say, is this a number or not? If it's not a number, then we're going to return something that says you have to put in a number, okay? And that's part of the algorithm. So effectiveness, right? Uh, so I think the point here is that it's something that the computer can do, right? Effectively, what we're talking about with these algorithms, you know, in real life, you're probably talking about some types of, or a lot of types of algorithms that is using computers and maybe some people to input into it, right? So, uh, you know, it could be someone at the DMV, right? You have to go in there and you have to show up to take a picture to get inputted to create your driver's license, let's say. Um, so those type of stuff. So it's basically you have an algorithm or a process to get your driver's license. And it's a mixture of like computers capturing information and a person taking your picture and putting it together, right? But in the case we're talking about right now, we're talking about algorithms for the computer. So the computer should be able to take each step and do it, right? Maybe it's to add some numbers together or whatever. It's not going to need some extra guidance from a person to do its work, right? So that's what we mean by this for the algorithm, okay? So effectiveness, okay? And you know, sometimes I look at what this is saying with the algorithm is almost like levels of abstraction. So over time, we have libraries built up of different functions, right? Otherwise, we have to, you know, we have to specify all kinds of algorithms to tell the computer stuff that has been done 10 million times before, right? So in this case, like they're talking about a function such as add, okay? So if you want to do some more complex algorithm with math, let's say, you don't want to have to keep on specifically talking about an algorithm at a low level detail to add two numbers together. Um, that's not really a good use of your time, right? So over time, there's all kinds of math functions, right? You can think about in Excel. Look at all the functions in Excel, the things that it can do. So those are kind of built up. So then you can build an algorithm on top of all those functions, right? And assume that those functions are available to you to do things. That makes your life a whole bunch easier. It's more efficient and whatnot. So in some ways, I look at building up those libraries of different functions as a level of abstraction, right? So I don't have to worry about those details. It's already been done, and I just use it, right? In this case, the example is to add numbers together. Okay, so this is what it means by saying algorithms can be specified at different levels of detail. Okay, so this built-in functionality previously defined or known to the users. Okay, so it assumes like certain types of things are known to the user. And this is where, again, I'm going to come back to Excel. Excel has a whole bunch of different functions. There's documentation associated with, so maybe you don't know all these functions, but it's there. And then as you scroll through it, you can say, oh, that looks like a function that I can use. It'll tell you like what types of inputs go into the function, what its calculation is going to do, and then you just go and use it, right? So then you don't have to rebuild that function from scratch, okay? Now this part where it says algorithms can solve the same problem differently. Just think about when you guys were doing the numeric conversions, right? There was a couple of different ways to do the conversions, and I think we tried to give everyone some freedom on to pick the best way to do numeric conversions that they felt comfortable with. But at the end of the day, the conversion, the output had to be the same. You can't convert one number to another number, end up with different solution depending on which algorithm you use, right? So although we may use different algorithms, the answer at the end has to be the same, right? So I'll give you an example of that in a second, okay? Okay, so this is something that we sort of kind of used to do in class a little bit. Obviously, we can't do that because we're doing a lecture now. But let's walk our way through it. Just imagine we're in a classroom and you would stand up. And when I say stand up, everybody stands up. You assign yourself the number 1, okay? And then you find someone standing. It could be someone right next to you, right in front of you, behind you, whatever, right? And then you add your number to that person's number and store the result, right? Store the result, I guess, in your brain, right, somewhere, right? So you found someone. You add 1 and 1, and you get 2, right? And everyone is doing this around the room, and it's different people, so you can't overlap. You can't have 2 people pointing to the same person, okay? And then one person sits down, and one person stays standing. Okay, so presumably the one that's standing is also holding on to that number, right? Holding on, in this case, holding up to the number 2. Okay, and then if you're still standing, go back to step 3, which again, you find someone else, and then you add the number, right, and so on and so forth. So this algorithm doesn't actually make clear, which it should. It doesn't make clear that the person standing up is the one that's storing that number, right, or where the number is stored. It could be stored off on the side somewhere on a whiteboard or something, but somewhere the number has to be stored, right? But if you think through, what is this actually trying to do? Ultimately, everyone's going to be sitting down, right? Or it'll be down to like 2 people or 1 person, right? And so because everyone was taking a number 1 and you kept on just adding and adding and adding, you can imagine, or if you really think about it, what's really happening is you're actually taking account for the number of people that's in the room, okay? If that's not clear, like just let me know later. But if you think about it, that's what we're doing. We're counting all the people in the room by doing this. Okay, so that's one algorithm. That's one way to do it. Now, I could do something different. Maybe I stand up and I say, okay, everyone is going to pass their number, right? We're still going to have everyone pick their number to be 1. But everyone is going to look to the right, right, and get a number from the person to the right, okay? And then they're going to add it to their own number, right? And then they're going to pass that number over to the person on your left, okay? And then once everybody moves as far as they can to the left in that row, then the person that's going to be in the bottom, the front row, is going to turn around and pass the number to the person behind them, the row behind them, all the way up until they get to the top. Okay. Now you can see that that should end up with the same number, is to add up the total number of people in the room. So it's a different algorithm, but the result should be the same. Okay, so let me come back to algorithm fact 3, right? So you can solve the same problem differently with different solutions, but the solutions have to be equal, right? And I guess that should make sense, right? Um, and the last thing I'll finish up with is just this, and I'm going to start off with this with the next lecture, right? This is the friendship algorithm, and we're going to step into this part here. You can see all these little flowchart shapes and whatnot, and that's what flowcharts are going to be for the next lecture. Okay, so I'm going to pause here. We'll pick up a new lecture on flowcharts soon. All right, thank you.